I want to welcome everyone to the Claude Hocott Lectureship in Petroleum Engineering at the University of Texas at Austin. Our speaker today is Dr. Michael Pyrcz, who joined UT as an associate professor in the Hildebrand Department in 2017 after 13 years working at Chevron. He teaches subsurface data analytics, geostatistics, machine learning, and many of his lectures are online and available for your own personal edification. One interesting note at UT, Michael is a PI in a freshman research initiative in energy analytics in the College of Natural Sciences. And before I hand it over, I have one last thing that I want to add, just a little interesting tidbit of note here is Michael and I are both from the Great White North. He's a little bit further north than me in Canada versus Minnesota, but what I recently realized when I was reading one of his posts is that we both had similar tasting cool cars when we were younger. So here's a picture that Michael posted of one of his early cars, the Mustang II, which was a sports car only in name. It was Ford's attempt to try and destroy its reputation. But I just want you to know that Michael's not the only person that had really hot cars when they were a kid. And so here's my Datsun B210 that I had when I was in high school. And one of the things you should note, that lemon yellow color suggests the quality of the car. So anyway, so I just thought that was an interesting thing that Michael and I can share, is that history of some pretty questionable cars. So anyway, I'll pass it off to Michael now.
All right, thank you very much, Chair Olson, for the introduction. I do appreciate that. In the defense of the Mustang II, if I may, would we all agree it's a cute looking car? It has some kind of nice curves on it.
I don't know.
It's better in the 80s. Come on, it's better in the 80s, John. And in case anyone's wondering, I did go to high school much later. I was actually kind of quite poor, and so that was the best I could get, was an old car. Okay, so what I'm going to do today, and I really appreciate this opportunity. Thank you very much to everyone attending. I'm going to give my AAPG Distinguished Lecture talk. And so I'll use the term geoscientist from time to time, but it is engineering and geoscientists, of course, target audience for this. So I'll give that. Now, what's my motivation? Well, talking about data analytics and machine learning, knowledge and trying to share with people, really what I'm trying to do is I'm trying to build new digital competencies for engineers and geoscientists, get you ready for the digital transformation. And I'll comment more on that in a little bit. In addition to that, let me get my laser pointer. I want to demystify data analytics and machine learning, kind of provide you with anti-baffling defense. And I think people do baffle in this area. I want to help you so that that doesn't happen to you. Share benefits and limitations, make you into an informed consumer. At the same time, I want you to be critical, and I will be kind of grumpy about it. You'll see that. Provide useful ideas and concepts, invite you to try it out. In fact, spoiler alert, when I show a bunch of workflows and examples at the very end, I will point you to my GitHub account and you can run them for yourselves. Repeatable research. You can try them out too, and let me know what you think. Let me know if you learned something from it. I think it'll be fun. Now, usually when I go places, they don't know me as well. So I do kind of a little about section about me, I got my Canadian Northern accent there. I'll just quickly make a couple of comments, pointing mainly to the resources that I share for anybody here who might be interested. I'm going to talk about data analytics and machine learning prerequisites. We got to define some terminology, get us all on the kind of understanding each other so we can move forward. Then I'll talk about energy data analytics and machine learning and how it's different, give some examples in energy, and then I'll talk about best practice. I'll go back to the fundamental ideas of data-driven workflow construction, what are good ideas for building models, and maybe not so good ideas. And then I'll show off some of the research from my students at the fine University of Texas at Austin. Hook 'em, and I would have done that even if I was anywhere else in the world, because you guys are awesome. I'm glad to be here. Thank you very much. All right, so just about me really quickly. If there is a student in this meeting who has not met me and just seen my name, remember, just say it like Pyrcz. That's good enough. My family spent 100 years in Canada and we've lost the ability to pronounce our last name. I've met Ukrainians who tell me we say it wrong. We're okay with that. I have practical experience. Everything I show you today, I've done in the field. I know how it gets done, and I teach a lot in industry, so I get to see what they're doing. I have an open door policy with my students. I have a lot of people drop by my office. Well, send me an email now, right? But drop me a line. People do contact me all the time. And I do have a background in this. In fact, I really enjoyed my career in industry. And part of the reason I'm here is because I love to teach and I really do want to give back. So I am very active on outreach, social media, professional organizations. As Dr. Olson said, I have many lectures available on my YouTube channel. Over 20,000 people a month are viewing my YouTube channel now from all over the world. And you guys are welcome, check it out. On my GitHub account that's linked to my YouTube channel, I have many example workflows. Some of them are super interactive. One I coded up last week within 24 hours was seen by 110,000 people. So these workflows are really, I guess they're attracting some attention, and check them out, see if you learn from them. Let me know if you have any problems finding these resources. And my team here at UT includes 12 PhD students. We have a brand new consortium direct, and we're doing a lot of work in subsurface data analytics, geostatistics, and machine learning. Okay, I promise for the remainder of this talk, I will not brag. That was my kind of couple of slides. I hope it didn't sound braggy at all. Let me talk about data analytics and machine learning prerequisites. Let's get on kind of that equal playing field. We're ready to talk. A lot of people wonder, do I have big data? Am I working with big data? Am I a big data expert? Big data is kind of one of those buzzwords. Big data. You have big data according to the tech people if you have data with a combination of these criteria. Now, these criteria, they're all the V's of big data: volume, velocity, variety, variability, and veracity. Now, what's interesting is when you talk to the tech people, and I do go to tech meetups, and they'll say things like, well, if it fits on your laptop, it's not big data. I don't have that extreme view on it. I say if there's many data samples, it's difficult to handle, visualize, then you have big data. You meet the 1V of volume towards having big data. Velocity. Do you have a high rate of collection of new data relative to the decision-making cycles? Now, the tech people are snobby about this, and excuse me about that, but they think it has to be real-time data. What I say is, given the complexity of our decision-making, we have velocity. It's continuous acquisition relative to the decision-making cycles. Anyone who's ever worked on an internship in a subsurface asset team knows we're constantly running to keep up with all of the new data, the new wells that are drilled, the new seismic processing, the new interpretations from the stratigrapher. Exactly. We have velocity too. Variety. Data from various sources with various types and scales. Oh my gosh, we win in that. We go all the way from pore spaces. I hope Dr. P is here, Dr. Prodanovich and others who work at the pore space, all the way up to the basin scale, the drainage radiuses and beyond to basin scale. We work across all scales with various sources. And variability is very interesting. Data acquisition changes over the project. I've worked with project teams who start in exploration with two-dimensional seismic. Then we move forward and we shoot 3D. Next thing you know, ocean bottom nodes are going in and we got 4D seismic. We have to integrate all of that together. We have variability. And finally, veracity. If you attend my classes, you know I'm kind of cranky and I'll repeat things over and over again a little bit. And one of those things I'll say a bunch of times is none of your data is certain. It really is. There's uncertainty in every type of data we work with, and we have issues with accuracy. So I say we win. In fact, I go further. I say energy has been big data long before tech even learned what big data was. And you might think I just kind of talk tough like that. I met with Google about 1.5 years ago, and I told them that. That was a lot of fun, in fact. So I do tell the tech people this. Statistics. Let's go ahead and define some terminology here. I'm going to encourage you to update your CV shortly, so there is purpose to this. Statistics, it's all about collecting, organizing, interpreting data, drawing conclusions, and always pointed towards the decision. What I tell people is if you don't impact the decision with all your work, you're not adding value. You really do have to impact the decision. So everything you do, line of sight to the decision. Geostatistics is a branch of applied statistics It has the additions of a focus on the spatial geologic context, geoengineering context, may I say, the spatial relationships, the volumetric support, and uncertainty. So if I drew a Venn diagram, I would make statistics like this, and geostatistics is an applied subset of statistics. Now, a lot of people hear about data analytics, and there's kind of this buzz thing around everybody's got to do data analytics now. You look up the definition online, what you're going to find is something about analysis of data to support decision making. Really weird. Doesn't that sound similar to statistics? In fact, what I suggest is, in fact, data analytics really is the good use of statistics, visualization to support decision making. So if you do a good job on statistics and all the stuff I teach in that PGE 337, then you update your CV. You're doing data analytics. Now, big data analytics, what is that? Well, it's the process of examining large and varied data sets to discover patterns, make decisions. All right, fine. We talked about big data. We should be comfortable now. Spatial big data analytics is when you have the expert use of spatial statistics, in other words, geostatistics, on big data to support decision making. The one regret I have in life is that I did not write that book. My book was not called that. I should have done that. There's an interesting book on the topic, spatial big data analytics. And so you'll see that if you have the overlap of big data and you work with the spatial context, which guess what? We are all about spatial context in the subsurface, then you're doing spatial big data analytics. Put that on your CV. That sounds epic, okay? Now, let's look up machine learning. Let's define that so we can move forward and talk a lot about machine learning. If you go to what everybody does, the Wikipedia article about it, you're going to find a quote like this. Is the study of algorithms and mathematical models. It's a toolkit. It's not just one method. It's a group of methods that computer systems use to progressively improve their performance on a specific task. It's learning. That's interesting. Improving its performance. Build on mathematical model on sample data known as training data. It's improving by learning from data in order to make predictions or decisions without being explicitly programmed to perform that task. This is the idea of generality, that it can solve problems for which it was not programmed explicitly. You know, machines that can win at chess without being taught specifically the rules of chess, but they learn them on their own by observing chess games. It's like that. Now, what's really interesting is that many people stop there. If you read right through to the bottom of the article or near the bottom, you'll hear this quote right here. And when I read that, I hear Dr. Torres Verdin's words in my head. And it's the idea that where it is infeasible to develop an algorithm of specific instructions for performing the task. What does that mean? If you know the engineering physics, if you understand the geologic processes, you're better off using that. Don't trust the machine to solve the problem. There's reasons we're going to use machines, and I'll talk about that. But let's not forget that we're engineers and geoscientists for sure. Now, every time I say machine learning, since I've defined it, every time I say it going forward, I want you to think of this equation. Every time I say machine learning, imagine a function that can take a set of inputs. Now, these are called the predictor features. Now, if there's a kind of a statistics person out there who's a little bit confused, I'll translate for you. Independent variables. That's what we used to call them. We'll call them predictor features because it sounds cool and it's useful. Predictor features are going to be the inputs for the model. And we're going to use our function to be able to go to a response feature or features. And once again, translating for my statistics friends, I would say dependent variable or variables. Okay, so we're just going to build a model to be able to do that. Now, when we do this, there's really two purposes or modes of operation. The first one is inferential, and the second one is predictive. Let's define both of those. What is inference all about? Inference is about looking at the system and trying to understand it. Looking at the predictor features and trying to understand the relationships, how they work together, how they vary together, are there sweet spots, what's the direction of the relationships, and so forth. Now, if you're still having trouble with inference, think about inferential statistics. And a basic definition would be, given a sample, describe the population. Now, for example, I could go ahead and say, I took this American dollar. I did not know we had American dollar coin, but I guess we do. And I could flip this 10 times. And I might happen to get 3 heads and 7 tails. If I ask you the question, what's the probability the coin is a fair coin? That's inferential, using the sample to say something about the population. Now, what is prediction? Prediction is going the opposite direction. Given our knowledge about the system, now let's focus on getting the very best estimate of a new location, a new value, a new sample, in fact. So we estimate this function f hat is a representation of the natural system, our best estimate of the natural system, to get the most accurate predictions of the response feature. We're focused on getting the most accurate. That's what it's all about at this point. Now, if you're trying to understand that, let's go back and think again about what predictive statistics are all about. Given an assumption or model about the population, predict the outcome in the next sample. In other words, I tell you this coin is fair, and you can trust me. I'm honest. This is a fair coin. Go ahead and tell me what's the probability of 3 heads and 7 tails. You see how that's a predictive model. Now let's talk about the 2 different types of models we're going to build with machine learning. We have parametric and non-parametric models. The parametric models are interesting. In fact, we make an assumption about the functional form or shape of the natural system. This F, we assume we know something about it right off the bat. And then we gain from the simplicity of the advantage of only having a few limited number of parameters that we need to actually try to calculate or fit, and we'll talk about that. For example, if we had a phenomenon like this is Z, elevation, this is standardized porosity, and you can see that there's the experimental data we have to work with. And if we go ahead and we try to fit a linear model to that phenomenon, it's beautiful. We only need 1 constant term and 1 slope term. We can build a very simple model, 2 parameters, cover the whole thing. But we can get it totally wrong. This phenomenon is not linear. We have a much greater risk that we just don't fit the natural setting indeed. Now, a non-parametric model is different. It makes no assumptions a priori about the functional form or shape of the natural setting. It's more flexible. It learns the shape from the data, and so can fit a whole variety of different types of problems. Less risk that your F hat is a poor fit. In other words, the estimate model is a poor fit for the natural setting. Now, the problem is, you know, there's no free lunch, right? Typically, you need a lot more data for an accurate estimate of a non-parametric model. In fact, what I tell people is if you're working with non-parametric models, please remember, that's actually parameter rich. Usually, if you look at this model right here, it's a decision tree model. Every one of these assigned value, constant values, and all of those thresholds are parameters. Indeed, there are a lot of parameters in this model compared to our linear regression model, okay? So you'll need more data to be able to estimate those model parameters. Okay, I'm gonna show you in 1 slide how you do machine learning. I still think it'd be important for you to take my course and so forth. Okay, I see my internet connection has a little bit of an issue.
Yeah, you might repeat that last sentence, Michael. I kind of missed it.
I'm just having little hiccups here today. Let me know. Thank you very much, Dr. Olson. Let me know if I cut out as we go along. We're good now?
Yep.
Okay, thank you. Appreciate that, Dr. Olson. So I'm going to take all of the training data. I'm going to take my model, and I'm going to get the very best model parameters so that I minimize the error at the training data. This is fitting the model parameters to the training data, training the model parameters with the training data. Now, I'm not happy with just one model. I'm going to take this model, a 1st order polynomial, and I'll augment it with another model, a 3rd order polynomial, and a 5th order, and a 7th order. In other words, I will train an ensemble of models, all with different degrees of complexity and flexibility. Then what I'll do is I'll take those very best models fit to the training data, and I'll apply them to the testing data where I know the answers, but I remember, I threw them away, I didn't look. So I bring them back now, and I assess the performance of my model with the withheld testing data. So these solid circles are my testing data, and I can evaluate. And I'll look at the error. These are just the error distributions right here. And I would pick the degree of complexity. The model that has the very best fit with testing data, and that's my model. Okay, so what have we done? We've trained model parameters, and now we've tuned model hyperparameters. But let me define those terms now, because I've used them a couple times. First of all, what are model parameters? It's not a big deal. For the case of a third order polynomial, the B3, the B2, the B1, the C, these are the model parameters. And of course, we know you change the constant term, you can make it go up and down. You change the other parameters and you can make it change its directionality, convexity. You can really change it quite a bit. It's pretty flexible, right? These are the model parameters and they are trained with the training data during that training phase. The model hyperparameters are very different. If you're trying to distinguish between parameters and hyperparameters, imagine the case of, does it change the complexity or flexibility of the model? That's what you ask yourself. And if it does, it's a hyperparameter. In our case, it's the decision between a first order, third order, fifth order, or seventh order polynomial. That's my model hyperparameter. Okay, so that's what I'm going to tune with the withheld testing data. Now let's just do a thought experiment right now. Everybody just answer in your heads. If I was to pick the model that got the greatest accuracy at training data, would I pick the first order, the third, the fifth, or the seventh? Which one of these has the best accuracy at training data only? Now, I think you'll see very quickly that with a sufficient level of complexity, you can perfectly fit your training data. That's very dangerous because look what's going on at the withheld testing data. You see that? That is quite an inaccurate model. I don't know about you, depending on the height of your monitor, this function is probably punching a hole through your foundation right now. You see that? It's just going right off the bottom of the screen. That's quite inaccurate at the withheld testing data locations. So this does raise some interesting questions or comments. At the end of the day, we really care about our machines, our models, being accurate in testing with withheld data. Why is that? Because we really want to check the real world accuracy of our model. How will it perform when you're using data that's reasonable, but wasn't used in fact to fit the model? Now, it turns out if you wanted to assess the expected statistical expectation, test mean squared error, and this would be the term right here, the expected value of the square of the truth values at the response feature, y, for naught, which are all the withheld testing data locations, minus all of the estimates from your function using all of the values for the testing predictor features. If you were to go ahead and try to calculate that, expand the quadratic and break up each one of the terms, you would get to this formulation right here. It does introduce some interesting ideas about additivity of variance, which is very, very powerful and useful to us in statistical modeling. First of all, you'll notice there's three components of error: model variance, model bias, and irreducible error. What does that mean? Well, model variance is due to sensitivity to the data set. In fact, if you think about it, our linear regression model, if you change the data, it will just move around a little bit. But the seventh or ninth order polynomial, if you change the data a little bit, it'll whip around. It's very unstable. It'll have a lot of model variance, sensitivity to the data. Model bias is like the opposite. A linear regression model will in fact have high model bias because it's not flexible enough. It's an approximative model. Okay, so let's look at this plot. We have model bias as we go to a more complicated model, like our seventh order, ninth order polynomial. We'll have more flexibility, that error will drop, but the model variance will ramp up. Irreducible error is due to missing features or limited samples. You know, we don't sample everything. We don't see every combination. It's a problem of the data. The world's most famous machine learning experts can't come here and reduce irreducible error. It's due to your data. And so it's constant. It doesn't change with the complexity of the model. What is overfit? Overfit is really an issue when it comes to machine learning, specifically complicated machines. What it's all about is if you plot the summation of all of those error terms, you'll find you'll get this type of a function right here, or behavior right here. And what you'll find is that as you increase complexity in testing, you should see the error go down, and it'll probably come back up because of model variance. If you look at the training error, it will keep dropping, because with training data, you can actually get a more and more flexible model. You'll reach a point where you'll perfectly honor all of the training data. When you reach a point where the error in testing is going up while the error in training continues to go down, you're in the zone of overfit. In other words, you're fooling yourselves. You've just fit all of the data. Overfit is really interesting. It is often related to the noise in the data. You're starting to the idiosyncrasies of the data, and it usually means your model will not generalize to new problems well at all, okay? Now we've covered the prerequisite concepts. Let's make some strong statements about why energy is different. Good news for all of you, spoiler alert, it makes us very powerful in this area. It really does help us out. Okay, let's go ahead and check this. Okay, now, first of all, if you have not been welcomed to the fourth paradigm of scientific discovery, let me be the one to welcome you. The first paradigm of scientific discovery was experimentation, and we can find archaeological evidence of that going on for a long time. Egyptians were doing tons of crazy medical experiments I'm glad I wasn't part of. Second paradigm of theoretical science, laws of classical mechanics, electrodynamics, we start to figure out that we could fit or model or understand the fundamental expressions for things we observed in science. Powerful theory. Computational sciences, well, we recognize the fact that we dealt with heterogeneous systems that were too complicated to solve just with first principles. And so we got into all kinds of other areas trying to deal with heterogeneity. And the fourth paradigm of data-driven science, now what we recognized was we had all this big data, all this computing resources. We could work to detect patterns and anomalies in big data, artificial intelligence, and so forth. This is the fourth paradigm of scientific discovery. Now, what I want to mention is all sectors of our economy are being driven to a digital transformation right now. Deloitte did a study back in 2019. Actually, it was kind of cool. I got to be interviewed and talk to them about some of this. And what they did is they looked across the different sectors of our economy, and they found that energy was somewhere near the middle when it came to readiness with new digital technologies. Now, what's very interesting was that they found life sciences and healthcare were somewhat on the trailing edge, and TMT, tech, media, telecom, you know, the tech people, they tended to be on the leading edge for readiness. But every energy company I visit, and I do teach inside of a lot of companies, they're all working on this right now. Now, here are some of my biases I want to be honest about. I think we have opportunities to do more with our data, opportunities to teach data analytics, statistics, machine learning to engineers and geoscientists to add new capabilities. But what I believe is that the geoscience and engineering knowledge and expertise remains core to our business. I feel very strongly about that. I'll make a couple more strong comments around that. Something else I want to point out. When we got into the third paradigm of theoretical science, we did not throw away experimentation. This was all supported by the previous paradigm. And the third paradigm of computational science, anybody who's doing this knows that there's tons of empirical expressions. There's all kinds of theory built in. In fact, we rely on the previous paradigms. We continue to augment, and that's how I feel right now. We use the data-driven paradigm supported by the previous paradigms for sure. We do not replace the older paradigms. Now, let me also comment on data. There was a wave about 10 years ago towards companies going to really great databases and doing better with our data. Data preparation and work with the data is usually greater than 80% of any subsurface study. In fact, it's very interesting. That has not gone away. Even with all this machine learning, we still face massive challenges with data curation, large volumes of metadata. I'll define that right away. Variety of data, scale, collection, interpretation. Oh my gosh, transmission, controls, and security. There are so many issues when it comes to data. In fact, what I'd say is that we still have not solved many of these problems, and clean databases are really prerequisites for any data analytics and machine learning. We must start with this foundation. Garbage in, garbage out still remains in effect, even with machine learning data analytics. Let me also make a very strong statement here. I want to emphasize this. Energy is very different from any of the other applications that I've looked at when it comes to data analytics and machine learning. And so we need unique solutions. And this is part of our mission to support our industry and society. Sparse, uncertain data, complicated, heterogeneous, open earth systems. You know, Google, they don't have sparse data. They know exactly where you go all the time. They see your car driving around with your directions. They got amazing, exhaustive data. High degree of necessary geoscience and engineering interpretation and physics. Nah, there's not such a thing when it comes to you making purchases on Amazon. They don't have any physics they can use for that. Expensive, high value decisions that must be supported. It was costing about $150 million to drill a hole in the Gulf of Mexico. We can't do that if it's not supported and it's based on a model that can be interrogated. Now, to compare and contrast, let's consider a common application of AI, machine learning. That is a recommender system from Spotify. Now, I don't know who here uses Spotify, but this was the music that was suggested to me by the recommender system back last summer. Now, you'll notice I'm Canadian, so there is a bit of Canadian stuff going on here, like Neil Young and so forth. Because I'm Canadian, every once in a while, it recommends Nickelback. Now, I don't know here if anybody likes Nickelback, please don't be offended, but I'll tell you what, Canadians no longer like Nickelback. None of us do. And we're sorry about Nickelback. This is a case of a recommender engine getting it totally wrong. What is the cost of getting it totally wrong? Do I cancel my Spotify account? No, I just fast forward and move on with my day. It's not a big deal. In fact, that's an interesting thing. These decisions are completely low value decisions. It would make no sense to have a personal DJ sitting in my office all day helping me pick my music. That would be ridiculous, right? In other words, a lot of these workflows, a lot of these methods were designed to work in completely different areas of application. We got to be a pretty critical user, consumer, and developer of this technology for sure. Now let's go back to that idea of the three components of error in testing, mean squared error testing when it comes to our machines. You remember how we had model bias, model variance, and irreducible error, and they were additive. If we add them all together, we get the expected mean test squared error, this red line right here. What's really interesting if you look at it is it tells us something really valuable. The most complicated model is rarely the best model. And so when we work with machine learning, don't drive to complexity. And guess what? When you work with simpler machines, you have better interpretability. You can understand what the machine is doing to support your high value decisions. Now, anybody here ever seen the example of the dogs and the wolves? This is a very famous example. Ribeiro back in 2016 had a great publication, very short read, and spoiler alert, they cooked it. They intended for this to happen, just to let you know. What they did was they produced a machine to demonstrate an important concept. The first concept is, with advanced machine learning, interpretability may become very low. It may be very hard to understand the machine. Applications of a preferred workflow may become routine and trusted. Anybody ever done an internship in industry where there's a standard workflow? You ever stand up in front of your boss and not do the standard workflow? You got explaining to do. It makes your day a little bit rougher, okay? The machine is trusted, it becomes an unquestioned authority. We got to be a little bit concerned about that. Let's go back to Ribeiro's example. They took multiple pictures of dogs and wolves. They put them into a machine. It was a logistic classifier. And what came out of it was a probability of wolf, probability of dog, the complement. Okay, and so when they did that, this image came back as high probability of wolf. Now, I don't know if you guys are dog people, but I hope we can agree that's a husky. That's a great dog to have up in north, eh, Dr. Olson? And you notice that it's just standing there all happily in the snow. Now, what they did is they looked at that dog and they said, well, what made you get a high probability of wolf? And so they took, and because they were experts, they could actually say, tell us which pixels in the image give it that high probability. These are the pixels from the image. What did they teach the machine to do? See dogs and wolves? No. The machine learned to be able to determine if there was snow in the background. You see that? So here, this is something we've got to be really careful about when it comes to interpretability with these very powerful machines. We've got to understand how they're making their decisions. As Peter Haas said during his TED Talk, these machines do not fail gracefully. So we got to be really careful. There's a technology hype cycle from Gartner, and I show this to every company I go to. This is the trigger. This is where we have a brand new technology. It's been discovered. It's starting to be used. Expectation or visibility on the y-axis, time from the beginning of the technology. You'll see we go to a peak of inflated expectations. Then we go down the backside. This is depressing to the trough of disillusionment, up the slope of enlightenment to the plateau of productivity. Every company I visit, I ask them where they are. Where do you think we are? Do you think we're here? I have yet to see anybody say that we're there. In fact, everybody I talk to says we're somewhere like here, and once in a while I've got people down here. We are clearly in a transition, and we will move to a more stable use of the technology. We are facing hype right now. Guard ourselves from that hype for sure. We have to manage our communications. Now, what I suggest going forward, if you look up online, you say, what's a data scientist? And I've gone to companies where they say we need to have a lot of data scientists. This is what they think they need. They need someone with domain expertise, somebody with all of the statistics and data analytics knowledge, and somebody who understands all of the coding. That's what they think that they need to work with. Now, what I find in actuality when we see data scientists is they tend to be very low on the domain expertise. They tend to have some knowledge around the statistics, and then they can do some of the coding, but we definitely lose out in a lot of domain knowledge. And I think that's still the most important part of what we do. This is what I suggest going forward. I think we can graduate geoscientists and engineers with data analytics and machine learning capabilities, well prepared for data-driven knowledge, with data-driven knowledge to be able to contribute in our industry in a more sustainable manner. I think we can build capability in the existing geoscience and engineering workforce, but I still think engineering and geoscience remains core. That's my vision of success moving forward. Okay, let me talk about some applications of energy. I'll talk about energy data analytics and machine learning examples, applications. Here's some things that we can do that I think are great. Feature selection. I taught that in my machine learning course just last week. My students are working on it. 70 students right now working on an assignment on feature selection. We work with many possible features. I'm doing projects with many companies in which they deliver me data sets with 40, 50, 80 different features to work with. If we pick the very best, most informative features, that's half the battle. We improve model interpretability. Don't get me even started about the curse of dimensionality. It is terrifying. And we reduce model variance and improve model accuracy indeed. Simpler models. So we need to be able to work with the best features. Here's some ideas. There's a lot we can do with data analytics with various different measures, powerful measures that are able to determine the very best features to work with. If you learn this one lesson, I think this will be very powerful and can be used in all kinds of workflows for engineering and geoscience. I think in addition to this, automated clustering is very powerful. When we do work in high dimensions, it's very difficult to determine what is the best grouping, and we have to do grouping in the subsurface. We have heterogeneity, we have transitions, everything is not stationary. Those of you who have not taken the geostats course, I apologize. Stationarity means that things stay the same from location to location. They don't. They change. We got a group. And it turns out we need to work with petrophysical and geophysical properties, and we need to have agreement between the two. Methods for clustering can be very powerful and can enable workflows where we're able to determine the very best groups that are constrained by petrophysical and geophysical data. So automatic clustering can be very powerful. Simple methods like linear regression, I challenge all of my students if they do machine learning, hey, did you try linear regression? Did you try a simpler method to try to make predictions? I think we always have to test things against the simplest methods possible. And of course, if you do that, why not move to more complicated methods? Isotonic regression is really understated. It's a powerful methodology from the standpoint that we can put in different engineering constraints directly into the methodology. It's very, very powerful from that standpoint. Maybe we know there's a monotonically decreasing relationship between porosity and density, but we want it to be able to incorporate kind of non-linearities. We can use methods like this to be able to do that and incorporate our engineering knowledge. Of course, you go to higher order types models, polynomial regression, and so forth, we get more flexible. And of course, we can go much further than that. Rich regression, something people don't talk about too much, we can combine the idea of fitting training data with the idea of regularization. In other words, a regularization term that reduces model variance and with a little bit of an increase of model bias can be very powerful to deal with noisy data and get much more powerful prediction models. If we learn just a little bit incrementally into machine learning, let's consider methods with regularization. It gets us thinking about the bias and variance trade-off, those two components of error, very powerful. Now let me show you a couple of examples in 2 dimensions. I actually have 3 features, 2 predictor features, porosity and brittleness, a geomechanical property in unconventionals, and a petrophysical property right here. And now I'm trying to take my training data and I'm trying to fit models to make predictions of production. It's gas production, MCFPDs. And so we could work with linear regression. This is a no-brainer. A geoscientist will look at this and start drawing strikes. It's got a similar strike everywhere. It's a plane. You fit a plane. You move beyond that, you get into K nearest neighbors. I'll tell you what, anybody who's ever built a map knows how to do K nearest neighbors. It should be something innate to your knowledge base. In fact, what you're doing is a form of convolution, a moving window average. And so it's very straightforward, but what's very powerful is you introduce the idea of a hyperparameter. Your hyperparameter being K, the number of nearest neighbors. Higher K, smoother map. Lower K, it can become much more overfit to the data. Very powerful concepts and very simple, and we're machine learning. Now, decision trees are themselves quite simplistic. They really are very simple. They're a hierarchical segmentation, a binary segmenter, right? To form constant estimate or prediction regions. That's what it's all about. Now, while it's very intuitive and simple, these methods can be actually combined together or built into ensemble learner type methods like random forest. So tree-based ensemble learning of random forest is built in order to support or encourage diversity between the estimators. And the result is you actually defeat model variance and build very, very stable machines to work with. There are many classes of problems for which random forest is still winning. Very, very powerful technology. And it's just a small extension past the basic decision tree approach. Now, if you've gone that far, you can go one step further. You can start thinking about gradient boosting. You start solving the problem as an estimator on the estimator on the estimator, incrementally or slowly learning how to solve the problem. What's very cool about that is, in fact, it starts to become a form of gradient descent. And the fact that we'll use a little bit of the fact that we're going to use a little bit of stochasticity with Bootstrap, we can definitely turn this into a stochastic gradient descent. Those of you who work in optimization will start to see the parallels between machine learning and optimization. They're all over the place. Now, if there's any of you who saw these examples and want to try them out, they're available on GitHub, and I'll show you where those are. Let me make some general comments in my 5 minutes. I am aware of the amount of time I have left. I have 5 minutes left, I hope. And I'll go ahead and make some general comments about working in machine learning. First of all, fit for purpose modeling. I'm a geostats person. I've done reservoir models all over the world. Fit for purpose models means that you have the goal in mind as you design the model at all stages. You're going towards a goal. Now remember this plot right here, please. This is important. Fast, cheap, and good. It's a form of Venn diagram. If you look at it, what's very interesting is that it's not possible to have fast, cheap, and good all at the same time. You see that? You have to pick 2. You only get 2. Fast or cheap, cheap or good, good or fast, good and fast. That's all you get, okay? So now you have to make a choice. You have limited resources, you have limited time, you have limited people and their expertise. You have to balance that. Modeling for discomfort. Since we're going to do data-driven modeling, let's understand some of the best principles we learned from geostats about modeling the subsurface. Mark Bentley, a super cool dude over there in the UK, really like him. I met with him and we talked about this. Models can become a tool for verification of a decision already partially or fully made. This is modeling for comfort. You see that? We're just trying to kind of prove it to ourselves. Mark Bentley recommends that we model for discomfort. We should feel uncomfortable. Stress test our current concepts and the decision making. That's very important. And then this will help us identify upside potential and secure against the worst case. We need to recognize our biases at all steps. Mark Bentley, great paper. Check it out, 2015. The other thing is, remember, we need to build on a foundation of probability and statistics. Naive Bayes is all based on Bayesian statistics and all of its associated math. Here it is right here, the naive Bayes assumption based on conditional independence. All of that fundamental statistics is really cooked into machine learning. That's why James and all in their book actually call machine learning statistical learning, which I actually think is a great idea. It is statistical modeling. Remember the principle of parsimony, okay? Start simple, models must be understandable, interpretability is really critical. Scientific method, use scientific rigor, robust use of statistics, be very critical, try to disprove all of your assumptions, and be inspired by the trades. I have a brother who is a machinist. I'm telling you what, he knows his tools very well. My grandfather was a machinist too. And I'll tell you what, whenever you use a model or a method, make sure you treat it like the tradespeople. Learn it very well. Don't use anything as a black box. Getting started, tons of resources are available to you. I post an awful lot, even if you're not in one of my courses, but I do welcome you to join in. That would be fun. Coding. Remember, nowadays we're using things like Python, where really it's very powerful. We're building workflows. I code much less in Python and get much more done. I do have years of full stack development in C++. I would not go back to those days for sure. And a lot of Fortran in my past too. So if you want to try it out for yourself, all of those examples that I just showed of those 2 predictor feature models, they're actually in a well-documented workflow. You can open up in Jupyter and you can walk through them and try them out. Play with the hyperparameters, change the model, see what happens. Very powerful. Okay, I'm not going to go through this. If you need some type of a further encouragement for coding, I have lots of arguments for why you should do some coding in Python. And let me just, I'm about out of time. Let me show a couple examples really quick to show off some of my grad students. Wendy Leod's done really good work in spatial anomaly detection. Paper just accepted by Mathematical Geosciences. This is spatially aware geoscience and engineering integrating spatial data analytics for spatial anomaly detection. It's really powerful stuff. There is so much great opportunity for us to use our skills and build new tools that use our expertise. We're building entire subsurface models using machine learning right now. Hongong Zhou, some of his great work just got published too. And we're doing seismic downscaling, work with co-supervised with Dr. Carlos Torres Verdin, where we're actually, let me show this off. These are subsurface models conditional to seismic and wells that far exceed any subsurface models we could build in the past. These are very, very powerful models. And I won't go any further. Javier Santos, sorry, but we're making rapid split-second predictions of high-resolution velocity fields, intergranular scales. This is moving us truly to the idea of multi-scale modeling for the purpose of flow. This is very, very powerful stuff. Okay, concluding remarks. Data analytics and machine learning are providing new tools. They augment what we already know in our expertise. The fourth paradigm for scientific discovery is there for all of us to add value with our domain expertise. Efficiency and automation, engineers do more engineering. That's how I see it. Detecting anomalies, I think this is important. Know where to focus our professional time. Our professional time is expensive, you know. Finding new patterns, pose new scientific questions for our engineering inquisition, our studies of the natural phenomena. Assisted interpretation. Working with big data is hard. Machine learning will help us do better with these large data sets and new improved models, better integration of expert knowledge. I'm optimistic. I'm excited. I'll stop there. I'm over by 1 minute. Thank you.
Well, thank you very much, Michael. Since you lost a little bit of time in your connectivity, we can, if people want to ask you some, well, we have time for questions. So if people want to go back and ask you for elaboration, that shouldn't be a problem. So I will tell the audience, there's 2 ways to ask questions. You can chat, and Michael should be able to watch the chat, or I'll watch the chat for him. Or you can raise your hand and I'll call on you and you can unmute and ask your question. So I would encourage you to ask some questions about his examples since he didn't have much time to say much about them. But any questions out there? Oh, David DiCarlo.
Yep. Raise your hand, you get called on.
Yeah.
Let that be a lesson to the students too. Dr. Pyrcz, very, very excellent. But the thing that always questions to me is, I'd like to know one of these examples. Can you go into details of one of these examples? So this is all pie in the sky things, but if I'm sure most of these guys, the energy companies say, well, we hired these guys to pay millions of dollars for our core logs, we millions of dollars on our seismic and millions of dollars on our petrophysics. And why don't we just give it to data scientists to figure out the problem? That's probably what they tell you, right? I mean, more specific examples of where the rubber hits the road in actual geosciences. I just pick one. I'd be fascinated.
Okay. Well, and Dr. DiCarlo, can I start my response with some smack talk? Are you okay with that?
Of course, that's the best part.
Okay. So you guys know that last year alone, I taught in 20 different companies. Like anytime I'm not here, whenever I can, I'm trying to teach because I'm very much trying to be, kind of support and also, all that stuff. So anyway, I've had multiple companies. And when I say multiple, I mean like 5 or 6 companies specifically during these engagements say the following. Tech team from this tech company showed up, said they can solve our big problem with our data. Spent 6 months, maybe 3 months, came back, and either one of 2 things happened. Told us what we already know, or just failed to really deliver anything. I have yet to see a case where just turn this big, massive subsurface petroleum engineering, geosystems engineering problem over to tech has solved the problem. I'll tell you what, when I met with Google and we had a great engagement just about 1.5 years ago, their comment to me was, Michael, can you get oil and gas to listen to us? They're stubborn. They don't want to listen to us. We have all the solutions. They won't listen. Can you be the person to help them listen? And I told them this. I said, you need to listen more than you talk. They've been big data long before you knew what big data was, and they know the engineering, they know the geoscience aspect. So I spent more time smack talking than anything technical. I apologize for that. But let me make one comment right here. This is a great example. Here's an example where Javier Santos and the excellent Professor Pyrcz and I were working on this problem of, can we predict the very fine scale velocity field for flow in a grain pack? And I see Dr. Pyrcz is supportive. I appreciate that. And so what we did was we could use lattice Boltzmann, which was a very painful calculation to get a pretty good, accurate estimate of those velocity fields. And we threw it at convolutional neural net. Now, Javier Santos is great with convolutional neural nets, and he spent a lot of time on this. At the end of the day, the accuracy was terrible. It was unable to generalize. It just wasn't working. What we did was we sat down, we put our engineering hats on, and we said, what's going on? The convolutional neural net has a scale it's working at, and it's not able to see beyond that scale. It's not interpreting, it's not bringing in all of the larger scale physics. What we did is we came up with specific engineered features that captured what we know physically about flow. We know that there's a velocity profile away from the surface, that it becomes minimal at the surface location, maximal in the middle of the pores, right? We know that there's tortuosity, and that's very, very important when it comes to flow. And so we engineered these features, put them into the convolutional neural net, and we're at the point now of about 13%, 10% error in velocity, which is way more than you need in order to get really accurate scaled up permeability calculations.
You can basically you don't have to do the lattice Boltzmann. You can just take a picture, run your results from your convolutional neural net, and it'll just spit out a good permeability estimate.
Which we would treat as a flow surrogate for fast interrogation and modeling. And what our vision is moving to truly multi-scale flow, where now Dr. Pyrcz, who spends so much time in the very small scales, will now be able to map the impact of that cementation or those features to a larger scale. Dr. P is on the line. Do you want to say something?
Yes, and I'm going to note that those features have been known in digital rocks physics for a while, but just using the traditional statistics tool or the traditional correlations to relate those features to permeability were failing, whereas combined with convolutional neural networks, it actually produced a success. I would also say that this success is good right now in granular media and sandstones, once we start to go to truly heterogeneous media, so throw in a fracture in there or a bug or something of that sort, so we're moving to carbonates, we need to train it better, and we possibly need to improve the type of convolutional neural network that we're using. So it's not just a given, but that said, if I know that like for sandstones and so forth, and like with more training, I go to carbonates and I can actually use this to spit out a permeability result in a second time as opposed to 6 hours of computing, that's great. Right? So it does, again, go back to this, like know your engineering and use the most recent machine learning tools.
Now what's fascinating, if you talk to Dr. Foster, he's working on actually encoding the engineering physics directly into machines, which is very, very exciting. That's a great emerging field and opportunity.
And that's right now called scientific artificial intelligence, because artificial intelligence just learns from data. How do you make it obey physical laws and be constrained by physical laws? Yeah.
Thank you, Dr. P. Perfect.
So Micah, you want to look at the chat for the next question?
You bet. Okay, so we have, Dr. Torres Verdin, all right. What is the most exciting machine learning application that you know of in the geosciences so far, and why? You know, I can't help it. It's not my bias because you asked the question, Dr. Torres Verdin, but I actually think that your work with Wenpan and myself could be considered among the top. The reason being is that I have spent, well over a decade working on the challenge of full integration of the architecture, the geoscience knowledge, the complexity of the heterogeneity in the subsurface with all of the various data, sources of data. And this, to me, is a major jump forward to be able to capture the complexity of the subsurface. Now, when we get into all these other opportunities of being able to explore the latent feature space, efficiently explore the uncertainty space, and visualize it, to me, that's extremely powerful. So I get very excited about that. I think that's a candidate.
Since you mentioned that, Michael, could you explain just a little bit of what those pictures are? I mean, I know what they're maps of, but what's prediction, what's data, or?
Yeah, great question. So if you look here carefully, you'll see the specs. And so we have, now I'm not sure if the well data are exactly plotted here. They may be the specs, or I think they may not be on this plot. But we have a set of well data that tells us at each location what's the specific type of reservoir rock. Are they, and this is like a meander type of pattern confined within a slope valley system. And so we can identify whether or not it's more of kind of an oxbow lake where it's a kind of low quality cutoff, rapid cutoff, or is it more of an active channel fill, or is it more of these lateral accretion sets with all of their associated heterogeneities? What we're able to do with this modeling methodology is we can train the machine to understand these patterns. And then furthermore, we can train it to condition or constrain these patterns by local observations, and importantly, the probability, the soft constraints coming from exhaustive low resolution seismic. Now, if you look at the world of geomodeling up until now, the biggest step forward we've had in the last while has been multiple point statistics, and they still fail from all kinds of inconsistencies and inabilities to honor all of these kind of constraints, and they don't actually reproduce the right connectivity patterns. These are far superior for sure.
Okay, thank you, Michael. We got one more. I don't know if there's one more hand up or if Michael wants to answer one more question on chat, and then we'll officially finish. But like I said, you can, if Michael's willing to hang on for informal discussion, you can certainly hang on and talk to him.
So why don't I answer the question by Mohammed that I see right here?
Sure, that'd be great.
And the question is, what are the basic skills required by a petroleum engineer who have good knowledge of the domain but don't know where to start on machine learning? You know, what's very interesting is I'm on a mission. And my mission is this. I think you're almost there. I think you're very close. In fact, I've said this over and over again. I've said it's much easier to take an engineer, a geoscientist with great domain knowledge, and to augment the skills around statistics, data analytics, and the models, the modeling methods and the coding methods to make those models go. In fact, I think it's quite practical and achievable for people to gain these skill sets and be able to use them in practice. So that's my bias. I think this is accessible to everyone. Now, how do I know that? I know that because I've taught hundreds of working professionals, and I've seen them within weeks apply brand new technologies and add new value. I've seen, because when I teach and I work at all of those companies, I get asked all the time about who are the engineers coming online, who are finishing up, who has these skills. So I'm hearing the demand too.
Okay, great. Well, thank you, Michael. Everybody can virtually clap for you here. And I would suggest, if you want to talk to Michael now, I mean, I'm gonna close the session formally, but if you want to talk to him and chat with him afterwards, why don't you unmute your video so he can see who you are out there that are interested in talking. And I may jump away, Michael, before you get finished, but since you're a co-host, the session should persist, or at least Leah will stick around, I think, and have the session persist. So thank you very much. I really appreciate it.
Okay. And John, thank you very much for hosting. I appreciate the invite. If the session closes, I'll ask Leah to help me set up a new session, and we'll just keep talking.
Okay. As long as Leah's here, it should stay open. So.
Okay, good. Hey, thanks a lot, Dr. P.